Discover how a tiny change in a spring constant transforms harmonic oscillator energy levels. Welcome everyone. Today, we'll study how to apply perturbation theory to a harmonic oscillator. Let's get started. So in this question, 7.2, of course we run into the harmonic oscillator, which has the potential, which should be 1/2 kx squared, not kx squared, and the allowed energies are En equals n plus 1/2 h bar omega for n starting at 0. This is different from the finite or infinite square well where they start at 1. So point of clarification there. And we see that we have the classic angular frequency, which is k over m. Now suppose that the spring constant increases slightly. So k goes from k to 1 plus epsilon k. All right. A. Find the exact new energies. Trivial in this case, but expand your formula as a power of series in epsilon up to second order. Part B. Now calculate the first order perturbation in the energy using equation 7.9. What is H prime here, or the perturbed Hamiltonian? Compare your answers with part A. And the author goes on to say how, in this case, we can't use integration, so we have to use a friend from the past, and we'll see that in due time. But why do we care? Well, the friend from the past is the viral theorem, and we saw how that was for stationary states very important to us in energy levels because we saw that kinetic equaled the potential for those stationary states of the harmonic oscillator. Very cool. That was discovered back in chapter 3 though, so a long time no see. But here's a challenge to think of. In what physical way can you modify the spring constant? And what he says in the book is that, well, we could cool the spring, but what other ways could you think to modify or perturb the spring constant in a physical system? There's definitely quite a few, so I'm sure we'll have some good answers there. But as we move into this question, let's not forget that there is a free companion PDF to help you follow along. Access it using the link below. And if you find value in its content, you can have a direct impact on its success by liking, subscribing, sharing with a friend, or donating through Buy Me a Coffee. So with that, let's dive into this question. Cool. So this is pretty straightforward of a question. We just need to get organized and make sure that our bookkeeping is up to par. If we want to look at and find the new energies, where we see that E prime, or the perturbed energy, is equal to n plus 1/2 h bar omega prime, and we say omega prime because we were given a modified spring constant, and we saw that omega was equal to k over m. So since omega is primed, we know that that comes from the fact that the spring constant was perturbed, and this is the perturbed spring constant. Now with this, we could, go ahead and realize that we are distributing this k over m, or we could simply separate it in the square root, which is what we choose to do. Reason why is because now we're able to rewrite this in terms of the original spring constant and m, so we can plug in the classic angular frequency. So we get back to that, but in doing so, what we realize is that we have this square root of 1 plus epsilon. So that's the perturbation, is the epsilon. Okay, and from this, it's real quick and easy to expand this out in a series, so let's see how we do that. So expanding then using a Taylor series, although the book tends to use power series or writes them as power series, these are all just series expansions, and you can reference the link I have in the PDF to see how they do that using the Taylor formula with derivatives evaluated at 0, so on and so forth. But nonetheless, what we see here is that we get the same energy that we had before, just with the square root, and then we approximate that with the series here, but again, the problem tells us that we only want it up to the second order. So not too bad there, we've seen that before, pretty easy all things considered. This is cool though, because by modifying the spring constant, we get this new energy total, the new energy levels, which have the original energy level in it. So this whole thing here, that is the original E in that we had. And we just multiply this by the factors of the perturbation. Minus 1/8 epsilon squared, and so on and so forth. So that's pretty cool. We get the redundancy built in there, and we like that. That makes it easy to deal with. All those other fun facts. But nonetheless, we quickly see that that is the new energy levels. So we can move on to part 2. And what we said to begin with in this chapter was for perturbation theory, the Hamiltonian that we're looking at in the new one is the original unperturbed Hamiltonian with some weighted constant lambda with the perturbation in the Hamiltonian, something that perturbs the system from what its ideal case was in the unperturbed. And from that, we expanded it out in a power series. But from the power series, we then set lambda equal to 1, so we end up with h equals h0 plus h prime. And so we're really good here. This kind of makes sense. We're adding the perturbation to the Hamiltonian to get a whole new Hamiltonian. From that, we can quickly solve for h prime here and find out what exactly what the perturbation is. And so from that, we can use Viral's theorem and go ahead and finish this problem. All right. So going ahead and algebraically solving for h prime, we simply minus that h naught over, right? So the unperturbed, not to 0 power, but unperturbed. We see that we go ahead for the new Hamiltonian, we get 1/2 k prime x squared, and we have, okay, minus the p squared over 2m, both of them cancel with the unperturbed k constant, so we're good there. And if we go ahead and plug in all this stuff, because we know that the Hamiltonian is just the kinetic energy term and the potential energy term, but we modified and we're told that the new Hamiltonian was with k prime, so we can solve for the exact perturbation. And I think we can see that the perturbation was given as epsilon, although it was not explicitly stated. Here we can see why this is the case. So if we go ahead and plug in k prime equals 1 plus epsilon k, we can go ahead and distribute this 1/2 into the parentheses. Easy enough. You could also distribute the k and x squared, which we do next step. From that, we can quickly see that the 1/2 kx squared and the 1/2 kx squared from the green cancel away. Easy peasy. And that leaves us with the perturbation only with the epsilon factor. Okay? This was the original perturbation, because had it just been 1 times k, we would just have the original Hamiltonian. But because we had this factor of epsilon, that was the perturbation in this particular question. So without explicitly stating it, and we're just given a new potential, we see quickly that this is just due to epsilon. And then once we push epsilon out, we can rewrite this in terms of the original potential. So this makes it quick, easy, and painless to deal with. From this, we can quickly find out what the unperturbed, or rather that Vx is the unperturbed potential energy. So the first order energy correction is the expectation value of the perturbed Hamiltonian. So that's pretty cool. We get this stated really quickly, and we can plug this in. Now we need to evaluate this inner product, of course, in the Dirac notation, but we can't use integration according to this problem. So let's see how we can maneuver. Well, quite quickly you can see that epsilon being a constant can be brought outside the inner product. No big deal. And we're just left with the expectation value of V between two end states. And like I wrote here, this reads as the expectation value of the unperturbed potential energy in the nth unperturbed state with the correction factor of epsilon. So that's a great little translation for how to deal with it. But we know that the total energy of this thing in the unperturbed case was the kinetic term plus the potential term. But thanks to Viral's theorem from problem 3.37, we know that the kinetic term was equal to the potential term. So in this case, we know that we can go ahead and substitute that in for the unperturbed energy level, like we do here in the purple, add them together, we get a factor of 2. Solve for the expectation value, which gives you 1/2 En with the unperturbed energy level. So using this trick, we didn't have to do any inner product integrals for this expectation value, because we're able to take this expectation value for V and plug it in here for the first order energy correction. And doing so yields this final result, which is pretty hefty and pretty nice. We get the first order energy correction, which is of course the epsilon times expectation value, but we saw for what the expectation value of V was in terms of the unperturbed energy levels. So we can quickly sub that in, and we see that we get this thing right here, which is what we want. No big deal. But of course, we can also simplify this for the E0 energy levels with the perturbation effect. And in doing so, what we see is that this is the first order term in this series expansion from part A. That's pretty darn cool. Of course, keeping it in the bracket here makes that really easy to see. So with that, we solve for the first order energy correction and we're done. Now, if you wanted the total energy, you would have to add this energy correction to the unperturbed energy. So E total, or the new energy, would equal the unperturbed energy with the perturbed energy. And in this case, that's just to the first order. But you could go ahead and expand this out to however many orders you need to make the experimental data make sense. So with that, I thank you for watching. This stuff is going to get a little more intensive very fast, so I hope that you can get a grasp on what's going on. Of course, feel free to ask questions. That's how learning's done. This stuff will, although what we see right now is real easy and base level for the couple nice potentials we like, the infinite square well, the harmonic oscillator, there's a lot more to be done here, especially when we get to the degenerate perturbation theory, because we saw that those energy spectrums were degenerate. So a lot of linear algebra is about to come in, inner products, and so much and so on and so forth. So let's prepare ourselves for that. That being said, a massive thank you to my supporters for making this possible. I'm extremely grateful for your support. If you'd like to see more, you can also become a patron for free access to supplemental material, current and future projects, and one-on-one help, especially as the new semester is about to start. New content is posted weekly to fuel your curiosity. Books, notes, and other reference materials are found below. If you have any questions, please feel free to reach out. As always, thank you for watching, and until next time, stay curious.